right, so we are going to continue with our notes and have a little bit more information here, kind of some review, but kind of looking at working on some of these concepts that we've been discussing about normal distributions and density curves. And then we're going to extend the thinking. We're going to talk about using a formula that's referred to as the z-score or the standard score for some work also. And I'll explain a little bit about why we have to learn that and why we can't always just use the empirical rule. But to begin with, let's do a little bit of review. And yes, I would strongly encourage you to fill in your note guide as we are working on this. You can hit pause and rewind if you need to, I think. So you can get everything written in if you need to. I think it's going to be helpful to have this as reference for in your note packet. All right, so brief review up here at the top. If the standard deviation is blank, there will be less spread and a tighter, higher peak. And if the standard deviation is blank, there will be more spread and a wider peak. So if you think about it, if we know that less spread and a tighter, higher peak means we have a small standard deviation. And if we've got a wider low peak, then we've got more spread. So that means our standard deviation has to be large. So that's all that's getting at. Okay? I want you to notice what we are looking at here in this next section of the notes. It says a normal distribution can have any mean, and any positive standard deviation. And I want you to think about why it's important and why it should make sense to you that standard deviation has to be positive. So think about how we compute standard deviation, how we are looking at a distance from the mean out 2 points. So hopefully it should make sense to you that standard deviation always has to be positive. So these two parameters, mean and standard deviation, that's the mu and the sigma, completely determine the shape of the normal curve. The mean gives the location of the line of symmetry, and the standard deviation describes how much the data are spread out. So take a look at these graphs. If you notice, they are showing the inflection points on these, and that's also considered change of curvature, right? So that's showing how much, what the distance is for our standard deviation in each case. So I want you to notice the mean for each of these problems. So these first two, it's saying have a mean of 3.5. So it has the same mean, but if you notice, it has a different standard deviation. So standard deviation here, this curve is a little bit lower and wider, so it has a larger standard deviation. This curve is high and tight, and so it's got a smaller standard deviation. So similarly, on this last problem, we actually have the same standard deviation here. So the same look for the curve, but if you notice, they are showing that the mean is actually at a lower location down here on the number line. Okay, so it says, notice the curve A and curve B above have the same mean. Curve B and curve C have the same standard deviation. Remember, the total area under each curve is 1. Remember, that's one of the properties I told you that you need to be aware of and familiar with. All right, so question here, it says which normal curve has a greater mean, which normal curve has a greater standard deviation. So remember, when you see these normal curves, the first thing you're going to want to do is actually draw in, let's go to pink here. Draw in where that line of symmetry is, where your mean is, so you can compare those. So the mean for curve B is 12, and the mean for curve A is 15. So the curve that has the greater mean is curve A, but if you look at change of curvature here, so let's change colors. You look at the shape of each of these curves. We're looking for change of curvature. Obviously, the larger standard deviation is with curve B. Okay? All right, onward. So we are going to start to talk about standard score. So I want to give you an example. I apologize. Let me talk to you about the fact that I'm going to kind of interchangeably use the term z-score and standard score. They mean the same thing. They're referring to the same thing. So just be aware of that. You may hear me say z-score. You may hear me say standard score. So the best example that I can give you to understand the idea of a standard score and why we want or need to use a standard score or a z-score is the best application I can think of for you all at this time is the fact that you all are right in the middle, at least many of you. You're taking SATs, you're taking ACTs. So if we compare, if you choose to take the SAT, but you also choose to take the ACT, and you want to be able to compare to determine on which test you did better, we need some type of standard way in order to be able to compare these. And so this formula, this standard score or z-score formula, helps us do that. The standard score or z-score formula basically explains to us or gives us a representation of how many standard deviations above or below the mean a value lies. So where with respect to the mean, but we're always talking with respect to the standard deviation. And so it standardizes that score so that it makes it easier for comparisons. So I'll explain a little bit more about that, and when we look at some examples, you'll be able to kind of see that. So I just want to put a little note in here. I think it's going to be helpful for you to be thinking about the fact that an example of when we would use standard scores if we are comparing ACT and SAT scores to determine on which test you did better. The other thing to realize is that we can use standard score or z-score anytime. So even the problems where you used the empirical rule, we could also use the standard score. But we need to know about the standard score also because there are many instances where we can't use the empirical rule. So if you notice, I put a little note here. It says, used when not a specific 1 or 2 or 3 standard deviations above or below the mean. So the empirical rule only works if it's an exact 1 or 2 or 3 standard deviations above the mean. And I want you to think about the fact that there are many instances where we could have a value that's half a standard deviation above the mean, or 70.75 or 1.5, any number you think of, standard deviations above or below the mean. Okay? So the z-score or the standard score is going to be written with this z is equal to. So this particular value right here, this z is equal to negative 3.49. Because it's negative, it means it is below the mean. And this is saying that it's almost 3.5 standard deviations below the mean. So that would be about right here. So I want you to notice this first property that they ask you to consider, and it says the cumulative area is close to 0 for z-scores at this particular value. Cumulative area means from as far left as possible if we go up to that particular point. And basically what this property is telling us is that we're not seeing any values in that particular interval. Okay? The second property says that the cumulative area increases as the z-scores increase. So this should make sense to you. If we look at a z-score of negative 2.5, and we compare that z-score with 0.5, then for this negative 2.5, we are clearly below the mean, 2.5 standard deviations. And this z-score of 0.5 up here, we're half a standard deviation above the mean. So if you think of this as a number line, clearly as the z-scores increase, our cumulative area would increase. Because once again, our cumulative area would be saying if we compare the area from here and lower, that area would be less than this cumulative area from here and lower. So that's what that's explaining. Okay, let me get rid of that just to kind of clean that up a little bit for any other information I need to share here. And then lastly, it says the cumulative area, I'm sorry, not lastly, two more things. The cumulative area for z is equal to 0. Z is equal to 0 represents our mean. It's right smack dab in the middle of our normal curve. And so the cumulative area is going to be 50%, right? It would be from here and lower is 50% of the data. And that's what that means. And that's going to be at a z-score of 0. So right smack dab at the mean. And then lastly, the cumulative area is close to 1 for z-scores of z equals 3.49. So think about where 3.49 would be on this. That's basically saying 3.5 standard deviations above the mean. So we're way up here. And if we do the cumulative area, then we're talking from here all the way down in this entire shaded normal density curve. So if you think about it, it should make sense to you that our cumulative area for that, it's basically that we are seeing that whole density curve. So the area should be 1. Okay? All right, I want you to see how we use this formula. If you look in books or online for the formula, then it has it written in a much different way. It has it written using sigma and mu. So it says z is equal to x minus mu all over sigma. Now, what I've found is that students can tend to get confused on that. So when I talk about this formula for z-score, standard score, I always think of it and I always say it as observation minus mean all over standard deviation. It helps us understand a little bit more clearly where we're going to plug in the values. Okay, so let's actually look at an example of how we're going to do this computation. So notice on this particular example that we are given, we are told that we have a normal curve and our mean is 100 and we have a standard deviation of 6. So that means, let's make this a little bit bigger so I've got some more space to read this. So we'd have 106 here, 112 here, 118, and I would have 94 here, and what is it? 6. Okay, so 88 and then 82. So if I were to draw my normal curve, that is what it would look like. Now the issue is that this value of 95 that we're supposed to figure out is not one of these nice pretty values on our number line. So that is a hint that we have to use this z-score formula instead of using empirical rule. So I also want you to think about approximately where this would be, right? If we have a score of 95, that's right here. So it's just above 1 standard deviation below the mean. So it's below the mean, but it's not quite 1 standard deviation below the mean. So I want you to notice then what type of answer we get here for our z-score. So to compute our z-score or our standard score, we're going to do observation, which this is our observation of 95, minus our mean, and then all over standard deviation. So what we get, we're always going to compute our z-score to 2 places after the decimal. So we get that z is equal to negative 0.83. So think about that again. Think about what that's saying visually. It's negative, so it's below the mean. And that 0.83 means that it is pretty close. It's not exactly on that 1 standard deviation below the mean, but it's pretty close to 1 standard deviation below the mean. Okay? All right. And then it says, find the standard score for a student who gets a 110 on this test. So think about where 110 is relative to this. We're close to 2 standard deviations above the mean with that value. So to use this formula again, here's our observation of 110 minus mean all over standard deviation. And for this, we get that we are 1.67 standard deviations above the mean. I'm going to show you how we use the table here in just a minute also. But in the meantime, just think about what this is saying. We are 1 2/3 of a standard deviation above the mean in that example. Next example, we're going to do these 4. Next example, we're going to do z is equal to 90 minus 100 all over 6. And in this case, we get that z is equal to negative 1.67. So that means we are about right here. And lastly, 115. Well, on this one, we're going to be pretty close to 3. We're going to be between 2 and 3 standard deviations above that mean. Halfway in between. So think about that. So z is equal to 115 minus 100 all over 6. And so we get 2.5. It's positive, so that tells us that we are above the mean, and we are 2.5 standard deviations above the mean. So the next thing that we are going to want to be able to look at is how we actually use a table to actually come up with what the percentages are. So we're going to scoot to this next page. For this first example, I see that we are at z is equal to negative 0.83. So we've decided that that's about right here, and it's shaded lower than that. These values are always at that particular point and lower. And so we're supposed to figure out what percent of the data is shaded, or what proportion of the curve is shaded. So we've got to use a table in order to find that value. So let's take a look. On this next page, I'm going to show you visually that which I shaded, that green that I shaded, is 20.33% of the graph. Looks like a little bit more just the way I shaded it, but you get the general idea. So let's look at another example, and then we will be done. I'm just going to look at one other one with you. Let's look at the 1.67. So let's look at this one. Whoops! I goofed on that. I meant to highlight. Sorry about that. So there's my 1.67. At 1.67, we decided that was right here. And if we shade from here and everything lower, then that is the distribution has been shaded. So 95.25% of the values are at that point or lower. So I'm kind of trying to give you a few different ways that you can think about these particular problems. By the way, we have to remember to talk to Ethan about how he knows a little bit about standard scores and z-scores. So more on that later. All right, hope this helped. Bye. This is, if you notice, it says areas of standard normal distribution. So if you notice the way this is set up, right smack dab in the middle is, think of that as your mean. And so values over here to the right, the z values over here to the right are positive, and the z values over here to the left are negative. So take a look. Here's all of these negative values over here. Here's positive z values here. So we're progressing up as we move along here, if you notice. And here we're starting from the middle, and if we progress to the left to show how far below the x-axis we are going. So the first example that we looked at, the z-score was negative 0.83. So if we go to the negative 0.8 for the z-score, and we scoot over until we get to the column that has the 0.03, then we find that the decimal is written as 0.2033, or you can write it as a percent as 20.33. So for that first example, where we had that z was equal to negative 0.83, that corresponds to a percent of 20.33% of the values lie at that particular location or lower. So let's go back. Let's scoot over to the table, and a z-score of 1.67, think about what that means. We are 1 2/3 standard deviations above the mean because it's positive. So we want to move over to this side of the table, and we're looking for 1.6, and we want to scroll over or scoot over until we are looking at where the 0.07 is, where that lines up, to take a look at that. So if you notice that particular value, it says it's 0.9525. So you can write it as that proportion, or you can write it as a percent of 95.25%. Think about what that means visually. 95.25% of the graph or the